Have you ever wondered if the Earth is flat? I mean, obviously we can see mountains and stuff, but that doesn't necessarily mean it's round, right? I mean, we could be on this gigantic plane of flatness with random mountains jutting out and stuff. We don't have to be on a sphere. Who says we have to be on a sphere? I mean, without actually going to space, how can we even know that our planet is round? A nice big sphere floating through the sky. I mean, sure, the moon, or the sun rather, is round, and if we could see the moon, it's round too. We know that from pictures, but that doesn't mean the Earth is round, right? What is up, guys? My name is Andrew, and welcome back to Space Busters, a series where we do a bunch of crazy space busty things, just like Mythbusters. We bust myths and stuff. It's cool and fun. Today we're going to be determining whether the Space Busters planet is round or flat, or any other thing. You know, it could be a disc. You never really know, right? But we're going to be determining that without going to space. How the heck are we going to do that? Well, we're actually going to start running that way, and we're not going to stop until we're back here. Actually, no. While that is a way to determine whether the planet is round, I mean, who knows? There could be a portal over there that teleports you over to that side, so you never really know for sure, right? No, what we're going to be doing is a variation of an experiment that was done over 2,000 years ago by a fellow by the name of Eratosthenes. I hope I'm pronouncing that correctly. It's a Greek fellow. And essentially what he did is he found a couple of wells that were very far apart, and he was able to measure the shadows coming from the wells at the exact same time. The difference in the length of the shadows, as well as the distance that the wells were apart, allowed him to not only determine that the Earth is round, but also determine the circumference of the Earth with a very small margin of error. He was very close. It's very impressive. This was 2,000 years ago. It's seriously cool. So we're going to be trying the same experiment on space engineers, because, I mean, we haven't been to space before. We totally don't know whether the planet is round. So let's get this done. Now, the first thing we're going to do is we're going to calculate the speed that we can run. So essentially this speed right here. Since we run at a constant speed, we're going to calculate exactly what that is. Now, I see that we have a meters per second meter at the bottom left, but that's not very accurate. It's kind of going all over the place. So what I want is an average speed. And the reason I want this is because we're going to be using this as an average to calculate the distance we go between our 2 points. So let's get that speed. We're going to start at P1 actually. And what we're going to do, I'm going to use my phone. Here, let me make sure I'm lined up on P1 real quick. Okay, so 3, 2, 1, go. All right, timer started and we're running. We're not going to go that far, just a little bit so that we can tell it just roughly how fast we're going. Okay, this is good. Okay, I stopped them both at the same time. So let's look back. Looks like we went 78.1 meters and it took 7.88 seconds. So our speed is 9.911 meters per second. So that's good to know. That means we can calculate our paces, which is very nice. Okay, now that we have our speed, it's time to start our experiment. So what we're going to be doing is we're going to be creating 2 different towers. We're going to create one tower right here, and we're going to create one tower kind of over there, really far away. And we're going to have to actually calculate that distance by hand, which is going to be super fun. But we're going to create one tower here, one tower there, and we're going to be able to determine the angle at which the sun is hitting the tower by the shadow. And we're going to do that at both sites. And then from those numbers, we'll be able to calculate, you know, whether or not the Earth is round or what the circumference is even. So let's create our first tower. So we're going to create it exactly on P1, since that's a good indicator right there. So we're just going to stick it right there. And we're going to go up a couple of things so we can get a nice long shadow. And don't worry about timing, because what we're going to do is we're actually going to adjust the sun's position. Once we get closer to the time, we're going to actually calculate these, because the only problem with this experiment is you technically need 2 people. You need one person to calculate the length of the shadow here. At the same time, one person calculates the length of the shadow there, but I'm only me. So we're pretty much just going to teleport from one point to another and calculate the shadows at roughly the same time. So here we are. Let's put a second position right here. We'll do, actually, do we need a second position right there? No, we actually don't. We can just calculate here. So 13.8 meters is the height of the first tower. Okay, there we go. We've got the first tower built. It's time to make the second tower. Now, I actually went into spectator camera and I marked a location here because that has the least mountains. The problem with counting paces is mountains can completely screw it up, especially since we're using time to determine how far we've gone. So if our time gets screwed up somehow, like if we stop, it's going to screw up the measurement. So we're pretty much going to have to run there in one fell swoop. And I'll time lapse that for you guys so you don't have to sit through the whole thing. But for me, it's going to be super fun. Alrighty, you guys ready? 3, 2, 1, start running. Alright, my hand is on the Shift W, and they cannot leave that until we reach the here location. Now we can screw up a couple times. For instance, if we need to go around a tree, that's fine. Or if we need to jump off a cliff, which I think at some point we will need to, since there's a cliff in our future. But we don't want to screw up too many times. All right, I guess let's go into time-lapse mode, and you guys can see this in fast mode as we just sprint towards the here marker. So time-lapse, 3, 2, 1, go. Couple more cliffs. Now I do know at one point, oop, let's dodge around these. And I do know at one point there is this massive, okay. There's a massive cliff that we're gonna fall off, and I think it's coming up, so be prepared for that. I would like to say though, look how beautiful the environment is. I always love to like mention how nice Space Engineers is, but gosh, like 5 years ago, well, maybe 10 years ago, this wouldn't have been possible with the computing power. We're in a little crevice. Come on, get ourselves out. There we go. Okay, we're good. See, small deviations like this will not screw up our speed, so we're fine. Especially since it's an average. That's the main reason that small deviations aren't terrible. I mean, obviously they're better avoided, but they're not like game breaking. They're not experiment breaking. But yeah. Okay, here's the cliff that we're coming up upon. This is not gonna be fun. Jump. Oh, yep, we got it. Okay, and jump over this one. Yep. And let's go around this. Oh, shoot. This is... okay. This might not be good. Jump. Okay, we're going much faster than normal. That's okay. There were some times where the game actually glitched for a second, so we lost a second or two on our time. But I think we'll be fine. We're in invulnerable mode, so we won't die, by the way. Oh, whoa, geez, we're really picking up speed here. I don't want to go too fast, because that will screw up the calculations. Oh, come on, don't bounce. Okay, we're still going good. We just need to get to the bottom of this cliff, and then it's a long straightaway to even out the time. Oh, we're gonna bounce. We're totally gonna bounce. Oh, okay. Jetpack that one. Okay, we're bouncing. Stop with the jetpack. Let's wait a few seconds to allow the time to catch up, and let's continue. Whew! Okay, so like I was saying before, it's all an average, so any small deviation like that, even that big deviation that was that right there, won't screw up our time that much, considering how far we've gone. So it's all good. That's a short way of saying it. It's all good. Don't worry. Let's continue this final way in time-lapse mode. We're almost there. I can see it. It's in that clearing. Almost. He could go all the way. Any second now. Okay. Stop the time. Whew. That was far. That was 30 minutes and 21 seconds. That's how long that was. 30 minutes. Alrighty, 30 minutes and 21 seconds comes down to be 1,821 seconds. And that coupled with the 9.9111 meters per second that we calculated earlier for our speed, gives us 18,048 meters that we traveled. Of course, that number is more than the exact point number because we went over mountains, and also, well, theoretically, the Earth might be round. So, obviously, going over the round part is a lot easier than going straight through the planet like this point would be doing. So, but we don't know that yet. Yeah, we have yet to calculate that. But right here, we're going to mark our P2 since this is our second position. So P2, good. Now we need to create our tower. Okay, so tower, we're gonna put it right there. We're just bring it up a couple. I don't know how far we want to go. Maybe the same distance as the one before, which was the 28 meters. Is that what it was? No, 13 meters. Okay, 13. That'd be down here somewhere. Yeah, that'd be right here. Oops, I fell. Plus 1 block. There we go. It's roughly the same. Yeah, 13.7 meters. That is almost exactly what the other one was. 13.7. The other one was 13.8, but yeah, it's just because some of it is, some of the block is in the ground more. So 13.7 for this one. Alrighty, now it's time to calculate shadows. What we're going to do is we're going to teleport back to the first one. So entity list, I think it's... Oh, there's too many. I've got too many towers. How many blocks do we put? 6 on each, I think, probably. So this one, that's the one we're at currently. This must be the one that we built earlier at L1. At P1, rather. So P1, let's teleport ourselves. That's us. At P1. Okay, now what I want to do is I want to make the sun go in the exact position over there, because that's where it was when we started. So we're going to go into admin controls again, and we're going to change the sun just a little bit. Oh, come on, we can do this. All right, I'd like to say that I made a mistake in my earlier calculations when I calculated the height of this, and it comes into play when we're going to actually calculate the shadows. Now, what we need to do is we need to calculate this all on a flat ground, and the only way to do that is to create flat ground, especially for the other one where it was kind of sort of on the side of a mountain. We need to create the own flat ground. So let's recalculate these heights. So we'll build up a couple blocks and recalculate our height. Don't need that one. This is looking good. Let's go down one, actually. There we go. So because we don't want it to go too long. Okay, so this is going to be 12.5 is our new height. So erase this one right here. 12.5. And we've already done the same thing for the other one. We've already edited it so it looks like this kind of, so we can actually calculate. Now let's manipulate the shadow by changing where the sun is, just so we can get it on this platform here, so we can calculate it well. Now in real life you can't manipulate the shadow. That's fine. But in this, we can actually manipulate where the sun is. So let's go ahead and do this. Okay, so we have the shadow right there. That's exactly where I want it. Let's calculate the length of the shadow. All right, so standing at the edge of the shadow, we can calculate this is 15.6, and we got to do this really fast. 15.6 meters. Let's go grab the other one. Really fast, really fast, really fast. If we don't do it really fast, the sun's going to change positions, and that's bad. Not this one, but this one. That's exactly where I want to be. Okay, so Control Enter, and we're here. Okay, calculate. Stand at the edge of this shadow. It's 29.1. So let's erase this one. 29.1. How fast is it changing as well? Okay, it's not changing that fast. That's good. It's kind of, you see how the shadow's growing? That's because the sun's going down. Okay, so one thing you might immediately notice is that the shadow distance of the first one, even though these are actually the same height, the tower's the same height, the shadow distance of the first one is 15.6 meters, and the shadow distance of this one is 29.1 meters. So if the towers are the same height, which they are, and the Earth is flat, then why are the shadows not the same length? Well, I mean, if the shadows aren't the same length and the tower is the same height, that must indicate that the sun is not in the same position for each site. So at position number 1, the sun is actually higher in the sky than at position number 2, and that's why you get a smaller shadow. If we model where the shadow is going to go, let's see. So since the sun's at that position and we have our tower right there, well, we get the shadow that we do as shown. Well, if the sun were actually higher in the sky, like say 10 a.m. or 11 a.m., you'd get a much shorter shadow just because that's how angles work. So whereas at position 1 all the way over there, the sun is higher in the sky, resulting in a shorter shadow, at position number 2 here, the sun is lower in the sky, resulting in a longer shadow. And that indicates to us that the Earth is not flat. It is in fact round. Or at least, well, we don't know if it's an exact sphere from this. You know, it could just be like a half sphere. We still don't know exactly if it's a sphere. But we're pretty sure that it's a sphere because everything else is a sphere, and at least we know it's not flat from this experiment. So now we know that the Earth is round and it's not flat, but how do we calculate just how big the Earth is? Can we do that with the calculations that we have, or with the measurements that we have, rather? Well, yeah, actually we can do that with a little bit of calculus. Or actually it might be geometry. I'm not sure. Whichever one uses sine, cosine, and tangent. Okay, so the first step to calculating just how big Earth is we're going to have to calculate the angle at which the sun is hitting this. And it's actually not as hard as it sounds. We can use the height of this plus the length of the shadow to determine just how angular, how much that angle is right there. So if we imagine kind of a dotted line going from the top of our tower to the end of our shadow, we can calculate the angle where the sun is hitting the tower. So if you've taken any sort of calculus or geometry, you might know this. We know the length of the opposite side. We know the length of the adjacent side. So which sine, cosine, or tangent are we going to use? Well, for this one, we're going to be using tangent. But since we know the length of the sides and we want to know theta, we're going to be using the inverse tangent. So the inverse tangent of the opposite side divided by the adjacent side is going to give us the angle theta at which the sun is hitting the beam. And that angle just so happens to be 23.246 degrees. Well, we can make the same calculation at the other side. So we want to know theta, we know the opposite side, and we know the adjacent side as well. So how big is theta? Well, we use the inverse tangent of the opposite divided by the adjacent side, and we get theta to be 38.704 degrees. Okie dokie, that was all the hard math in my opinion. That's the stuff I don't like touching. Thetas and stuff like that. Now that we know the two angles at which the sun was hitting the beams, if we zoom out all the way so that we can see the full Earth, the point on the left is our point number 1 and the point on the right is our point number 2. They're not that far apart, but we can actually use them to determine the circumference of the Earth. And here's how. So let's imagine the Earth as a pie, and we're going to make a slice of the pie. And the way that we're going to do that is we're going to imagine each of the towers that we built to go straight into the ground and to keep going until they hit the center of the Earth. This little section is going to be our pie piece, and the distance between the 2 points is going to be the crust of our pie. While using basic mathematical principles, we know that the full rotation of the pie is 360 degrees. So if we knew that angle theta of this exact slice of pie that we basically made here, and we also knew the distance that is the crust of the pie, we could use those to determine the whole length or the whole circumference of the pie. So that's exactly what we're going to do here. But how do we calculate the angle theta? Well, it turns out the angle of our pie slice here that we have is the difference between the two angles that we calculated. So if we subtract the second angle from the first angle, well, we'll get the angle theta that we want. So let's do exactly that. We'll take the first angle, which is 38.704 degrees, and we'll subtract 23.246 degrees, which is the second angle. And that gives us our theta to be 15.458 degrees. So if we do 360 degrees divided by this little theta for the little pie piece that we have, we're going to get 23.288, which means this is 1/23rd, I guess is the way. This is 1/23rd relatively of our whole pie. So now that we know how many little slices of pie it takes to make up a full pie, or how many little slices of Earth it takes to make up a full Earth, since we know the distance of our one slice, we can multiply that by how many we need to make the full thing. So our fraction of the full Earth, which is 23.288 times the distance between our 2 points, which is 18,048 meters, gives us a circumference of the Earth that is equal to 420,318 meters, which is pretty large, let's say. From that circumference, we can use a bit of basic math to derive the radius, which for our calculations is 66,929 meters. So how far off were we? Well, the actual radius of the Earth in Space Engineers is, or the Earthlike Planet, I guess is the proper name for it. The actual radius is 60,000 meters on the dot. So we were relatively close. We were off by 6,000 or almost 7,000 meters, which, I mean, obviously it could be better, but yeah. Could have been worse as well. So why exactly were we off? I mean, there could be a whole myriad of reasons for that. It could be anything from, you know, there were a lot of hills we had to climb, so that could have affected the actual distance. There were a bunch of cliffs we had to drop from, so that could have affected it as well. And there could be some human error in calculating the shadow distance. So any of those things could have contributed to the reason that we're 7,000 meters off. But at least I'm happy we're not 60,000 meters off, right? So the really cool thing about this experiment is that one very similar was conducted over 2,000 years ago when they didn't have computers, or they didn't have, you know, mechanical calculators or electronic calculators. They didn't even have electricity. They didn't have cars, they didn't have planes, they didn't have GPS, and these guys were able to calculate with a very, very close number to the actual circumference of Earth, which is super impressive. The other thing that's really cool about this experiment is that it's not complex. You can do this if you want to. Find a very long straightaway and a couple of very similarly sized sticks, and you can actually go and calculate the circumference of Earth. Just like that. I don't understand why there are so many people claiming that the Earth is flat when they can just do this simple experiment. You know, it'll take them an afternoon to do this thing. And they'll you don't have to fly to space. We didn't fly to space for this. I mean, we did at the end to show you, but we didn't do anything crazy. You don't have to do anything crazy. That's just how it is. You can calculate the circumference of Earth using just a couple of sticks in the shadow. Well, that's going to be the end of this one, guys. If you guys like this video, please hit the like button. Put your comments and your suggestions down below, especially if you know why I might have been off. I mean, I gave a couple of examples, but maybe you saw me do something that was incorrect, or maybe you saw like some error that I did. So if you found one of those, please comment that. Also, if you have an idea for a future Space Busters episode, please comment that as well. I'm really loving you guys' ideas. I have a spreadsheet full of, it's got to be at least 50 ideas. There's a lot of things in here. I pretty much, when I want to do a Space Busters episode, I just pick one off the list and I just like, all right, this is what we're going to do today. And today we decided to prove that the Earth is not flat. So that's always fun. All right, guys, I'll see you in the next Space Busters episode.